audio adapter. Okay, so now next presentation, Yeshi, thank you.
Good morning, guys. Welcome to the vertical presentation from AnDy team. Technically, the title of this presentation should be something like Integration of AnDy and iFeel Technologies, but our Scrum Master came up with a really cool title, which I couldn't resist but use. So the actual presentation of this is going to be something like how AnDy met iFeel. This is the outline of the presentation, where I begin with the overview of AnDy project with a little bit of background and the technologies we developed as part of AnDy project, which enable us to build some really cool applications. Then I'll briefly talk about the motivation behind the iFeel project and the overview of the project in terms of hardware, firmware, and different software architecture design choices we had to make in order to enable a tight integration with respect to all the AnDy technologies we developed. Finally, there are a couple of success stories which we were able to achieve thanks to this tight integration between iFeel and AnDy technologies. So to begin with, AnDy, as Claudia was pointing, is a European project which stands for Advancing Anticipatory Behaviors in Dyadic Human-Robot Collaboration. Technically, the project promises to use different technologies in order to give capabilities for complex robots like humanoids to control the physical collaboration through intentional interactions with external agents. So what it translates to is like really complex demos. And this is a picture from year one demo in Genova in March of 2018. Although we look super happy in this picture, behind the scenes we're very chaotic because the demo we are trying to achieve has so many complex things in place. So at the hardware level, we had a human subject who is wearing whole body motion tracking system and also wearing a sensorized shoes that contain four force torque sensors. And the subject is supposed to stand on this ground fixed force torque plates and interact with a complex humanoid robot, which is our iCub. At the software layer, we had C++ YARP modules, which were bringing all the sensor information from different hardware, and then try to implement some estimation algorithms like inverse kinematics for the human or stochastic inverse dynamics. And we are using components which are like ROS, RVs, that is outside part of YARP somehow, as real-time visualization. And we had whole body torque controller implemented in MATLAB Simulink. So if you carefully look at it, it's quite a complex system, and we're pretty much heading in a direction that's going to collapse. And thanks to the intervention from Luca Talipitra, who was a postdoc before, and Diego Ferigo, they did a phenomenal job in developing what we call a wearable library that offered really a nice set of sensor interfaces, which when coupled with the idea of ERP devices, enable us to wrap all this different heterogeneous hardware to package all the sensor information into a homogeneous data format, which we call wearable data, that can be communicated to network, which is ERP network. Basically, this gave us a good framework and template to refactor the human dynamics estimation project. And we also replaced all the C++ YARP modules, which were quite shaky at that point, into YARP devices, and then able to wrap individual devices such as human state provider with inverse kinematics estimation algorithm. And each device has particular functionality in the system. So thanks to this streamlined software infrastructure, we are able to realize some really cool applications, the most fundamental of which is this dynamical inverse kinematics, which is developed by Lorenzo. This runs in real time on even a complex model of human, which has 66 degrees of freedom. And this is the fundamental enabling technology that made possibility or real-time retargeting to whole body retargeting to complex humanoid robots. And we were also able to realize applications like teleoperation when coupled with whole body balancing controllers or walking controller. The other application is the extension of the fixed base stochastic inverse dynamics estimation, which was the work done by Claudia, to a floating base system. This fundamentally enables us to use this whole technology stack in outdoor applications such as sports or warehouse arena. Also, we continued along the directions of physical human-robot collaboration, where we tried to investigate how different quantities from the human can help the robot in performing complex tasks like standing up. More recently, we did this work, which we refer to as non-collocated wrench estimation, where the fundamental idea is to estimate the forces at links such as hands, where you do not have any direct sensor measurements, and try to estimate, try to reflect an object that the human is manipulating. And a direct application of this is a scenario where in warehouse, the humans often transport different payloads. And here in the visualization, you can see when the object is transported, we can see the shift in force estimates to the other subject. Now, we really had a lot of experience in the last in this duration of 3 years while doing all these cool applications like teleoperation, real-time ergonomic assessment, physical human-robot interaction, and more recently, like Claudia was pointing, adaptive piezo control, and also rehabilitation applications. One thing we really noticed is this heterogeneous hardware systems always translate to more development time. As an example case, we have Xsense and IIT Force-Dark sensor integration. Xsense is part of the consortium for AnDy. Technically, we are supposed to do a hardware integration of these two systems, which was not really easy. It was resource intense and time consuming. So we settled with just a software integration. And the next limitation is clearly in terms of hardware. If you take something like off-the-shelf hardware, for example, Xsense do not have any haptic feedback. It's simply an inertial measurement unit which doesn't have also other sensors like temperature sensors. With all these limitations, we're also noticing this emerging technology landscape where people are putting different wearable technologies to realize different applications for rehabilitation or real-time ergonomic assessment. At this point, we decided like, okay, we have a really cool software stack. It's time to build some hardware. That's exactly the idea behind iFeel project. In this slide, I'm going to simplify all the hardware and firmware work done by Enrico Gianluca. Please, I apologize already. This is just a bridging for the next slide. So bear with me. What is iFeel node? iFeel node is nothing but a piece of hardware that has two sensors, which is inertial measurement units and a temperature sensor. What we want to have is a bunch of these sensors distributed and a piece of another hardware, which we call iFeel Central Station. And they're supposed to send, all these iFeel nodes are supposed to send sensor information to the central station through a network, which we call iFeel network. And we designed like a proprietary communication protocol as part of the iFeel project. At this point, I really have to mention that the research efforts which went into iFeel U bracelet really pushed forward in setting up all the infrastructure for network and the communication of sensor information from all the iFeel nodes to the central station. So now moving on to the software architecture, what we have is the central station, which has USB transport capability that when plugged into a workstation, what we ideally would need is a way to package all the information from sensor nodes into a variable data format so that we can use all the rest of AnDy technology stack. For this, what we wanted is a C++ library with API calls that give sensor information from different iFeel sensor nodes, which are configured as part of the iFeel network. And this is exactly what iFeel driver is supposed to be, which acts as an SDK in order to develop new iFeel suite wearable device that packages all the sensor information from different iFeel nodes into a wearable data format. Now, putting all the things together, how we integrate with iFeel and AnDy technologies. At one extreme, you have this hardware layer where you have iFeel nodes as sensors, sending information in iFeel network to the central station. And iFeel suite wearable device is the one which packages all the information from iFeel sensor nodes to wearable data, and which we can use it to process, to run the estimation algorithms, which are part of human dynamics estimation project. One major component which we are missing at that point is the ability to send commands back to nodes. For example, each of the iFeel node has a haptic device. And at that point, we didn't have any actuator interfaces as part of wearable library. And this is something we recently did, which allows us to send wearable commands, which activate each of these haptic actuators that are present on the iFeel nodes. Now, let's look at some of the success stories. I think these visualizations are something which you saw from Enrico's presentation, John Lucas and Clarius, but please bear with me. Basically, we managed to put together three iFeel nodes that are configured to upper arm, lower arm, and the hand of a subject. And when we move it, we can see real-time visualization in Arvis here, which is the complete pipeline from hardware of iFeel nodes to the end of inverse kinematics, which is part of human dynamics estimation. The next one is the story related to sensorized shoes. The initial version of these sensorized shoes were a mess in the sense of their usability. They were quite limited, very fragile, and the gait was completely different from the normal gait because they're a bit heavy and clumsy to wear. We did tremendous work in this direction, and what we have now is, I feel, shoes which are completely wireless and very user friendly. At the same time, we managed to get the data frequency at the same rate as we used to get with the wired shoes. And in the visualization, you can see a kind of mixed demo where you have the data coming from Xsense as part of the motion data and the data related to ground reaction forces coming from wireless shoes. And the final one is again what Stefano presented, that's concerning the haptic feedback related stuff, where we use the haptic vibrators, which are part of iFeel nodes, and connected the application for skin contact detection to vibrate. And this is what we translated to an avatar experiment, where the teleoperator, who is Julio, strapped with this iFeel nodes, can actually feel the vibration as a direct reaction to the skin contact detection from the robot. And so, what's the future of iFeel? This is something again Danny mentioned. There is this new project ErgoCub, which is more realistic scenario, more like practical in the sense we are trying to adapt all the technologies we developed so far for real market needs. And naturally, we are going in that direction. So we're bringing all the AnDy and iFeel technologies together to ErgoCub. So finally, to conclude, this is the current core team, and I listed some of the contributors who contributed to most of the work I presented here. Thank you.
Any question? No. I have a question. Yes. I mean, what do you think that? What is the next piece of sensor you think that we have to integrate into iFeel right now?
I'm not sure if we can say a heater for that.
So the transducers, the heater.
I mean, why not?
Yeah.
For the another specification.
For the another specification. Yeah.
And I think the next big thing is definitely going to be the work of Italo in terms of having the stretchable material as insole. That would change the game.
Yeah, probably by, I don't know, making a new suit where all the stretchable is around.
And also multi-haptic, that will also be very nice.
Okay. Yeah. Okay, let's thank
you guys.
Yes, again. So now the agenda, Nuno,